So our starting point with this question is to do the empirical formula. So we do the normal thing with the table. So if we set up the usual thing with the elements across the top, copy the numbers down, can either be actual masses or percentage masses, it doesn't matter which. So we just copy down the percentages and divide them by the relative atomic mass so that we turn them into relative moles rather than relative masses, which gives us 5.41 and 3.5 and 6.3 and 1.8, and then we divide through by the smallest of those, which with a bit of luck gives us whole numbers, but in fact in this case gives us 3 and 3.5 and 1. So it's the usual thing, we think, right, well, if we multiply everything by 2, we keep them in the same proportion, but that becomes a whole number. So we do 6, 7, 2. Okay, so C6H7O2 is the empirical formula. But that's not necessarily the molecular formula. To find that, we need to compare that with the MR. So we calculate the empirical MR from this. And if we just add that lot up, we get 111. And then we go to the mass spectrum and we look at this peak, the one furthest to the right. It has a little tiny shoulder on it, remember, which is the C13 satellite, which we ignore, but this peak is the molecular ion peak, and the M over Z is 222, and that tells you that the MR of the compound is 222. It's really important that you spell it out like that. People tend to just say things like, I can tell from the mass spec that the MR is 222, and that's probably too vague. They'll say, yeah, how do you tell from the mass spec? So you say the molecular ion has an M over Z of 222, therefore the MR is 222. And of course the point about that's equal to 2 times 111, 2 times the empirical MR, and that means that the actual molecular formula is, we've got to double all those numbers. So C12H14O4 is the molecular formula. Okay, so that's the first important part of the operation, is to calculate the molecular formula, and then you can start looking at the NMR spectra. So looking at the carbon-13 NMR, which is this one, remember we look for 2 things. We look for the numbers of peaks and we look for their chemical shifts and what they tell us. So the first thing to note is that there are only 6 peaks altogether, although there are 12 carbons in the compound. So there's a lot of equivalent carbons, and we need to keep bearing that in mind as we're thinking about the structure. Looking at chemical shifts, this one is clearly C double bond O. This one is C single bond C, and this one looks like C single bond O, because that's the only one of the possibilities that's consistent with the molecular formula. And these ones could be either aromatic carbons or alkene carbons, but you can usually tell which by then looking at the proton NMR, because if it was an alkene you would probably get some alkene CHs, which would be between 4.5 and 6, and you can see there's nothing in that part of the spectrum. If it's aromatic, you get peaks between about 6.5 and 8, and that we do have. So these ones we can be pretty confident are actually aromatic carbons. So where does that leave us? Well, it tells us that we've got an aromatic ring. We've seen the possibility that we might have 2 of things because of the equivalence thing, but we obviously can't have 2 aromatic rings because that would account for all 12 carbons and wouldn't leave us with those. So we know we've got one aromatic ring from this, plus 3 other peaks from the 6 remaining carbons, and that strongly suggests, it doesn't prove, but it suggests that there might be 2 of each of these. But we can't tell that from the C13, but we can tell that we've got one aromatic ring, because 2 aromatic rings would add up to all 12 carbons and wouldn't account for that. So we're going to keep that in mind as we go to the structure. But the other thing that's really important is that there are only 3 peaks in the aromatic region. And that's going to be quite important later on when we're trying to figure out the specific structure, that we've got to come back to the fact that although there are 6 carbons in the aromatic region, there are only 3 peaks. So again, there are equivalent peaks within the aromatic structure. Okay, so let's go to the Proton NMR. And the first thing to look at are the peak areas, because those are interesting, because you've got a 3 and a 2 and a 2, so the total area adds up to 7, but you've got 14 hydrogens in the structure. That's really important, because that means you can't just say, oh, this is 2 hydrogens, this is 2 hydrogens, and this is 3, because that would only add up to 7. So what we can say is that the total area is 7, but there are 14 hydrogens in the structure, which means in effect that each area unit is equivalent to 2 hydrogens. So that area of 2 means you have 4 hydrogens there, 4 hydrogens here, and 6 hydrogens there. Because obviously there have to be 14 hydrogens altogether. And you have to remember that the peak areas, the spectrometer doesn't magically know how many hydrogens in an individual molecule are contributing to the peak. All it does is just literally measure the area underneath the peak. And you just have to remember those areas are proportional to the relative numbers of hydrogens. And so sometimes you have to say, well, it's not 2 to 2 to 3, it's 4 to 4 to 6, or 6 to 6 to 9, or whatever. And you can, as long as you know what the molecular formula is, that's not a problem, because you can work out what you have to multiply it by in order to get it to add up to the right number of hydrogens. So now let's look first at these peaks, which we know are the aromatic peaks. So we'll lump those together and call them A, because remember that the exam board stipulates that it will never expect you to pick apart the detail of what's going on in the aromatic region. It says that on the syllabus. So we don't have to worry about splittings or how many separate peaks there actually are within there. All we worry about is that those peaks collectively are the aromatic ones. And the key bit of information is that there are 4 hydrogens. And that's hugely important, because that tells us that we have an aromatic ring with 2 substituents, with 2 things stuck on it, which just leaves room for 4 more hydrogens. So from peak A, we can say that those are due to aromatic hydrogens, and you must explain how you know that by quoting the data sheet and say, right, it has an aromatic hydrogen shift, and quote the numbers, 6.5 to 8 ppm. Okay, you've got to stick to the script on this one. When you're talking about peaks, you've got to write down the environment and what range it corresponds to, so you can see, yeah, that fits. Okay, so it's got a proton shift, an aromatic carbon shift, and crucially, you have 4 hydrogens, because you have the peak area of 2, and you've already explained, if you wrote this down, that corresponds to 4 hydrogens, and that means that there are 2 substituents on the ring. And it's important both to write that down, because that's an important deduction, but also obviously to keep it in your mind when you're trying to work out what the structure is. Okay, so just by looking at that cluster of peaks, we know we have a benzene ring with 2 things stuck on it. Now that leaves these 2 peaks, and these have to be splitting each other. Remember that you can't get splitting between hydrogens within a benzene ring and hydrogens outside it. We talked about that before, but just to remind you why that is. So if you have a hydrogen here and a substituent there, say CH2X or whatever, obviously you can't get splitting between that hydrogen and those hydrogens because that carbon comes in between. So there are never going to be adjacent hydrogens, one within the ring and one outside the ring, because there's always that intervening carbon there. So that means that when we see split peaks which are not aromatic, that they can't be split by the aromatic hydrogens. They must be, in this case, because there are only two of them, they must be splitting each other. So if we label these peaks B and C, we know that they must be coming from adjacent sets of CHs. Now this pattern that we see with peaks B and C is one you've seen many times now, that you have a triplet and a quartet splitting each other with relative areas of 3 to 2, and you've seen that lots of times because that's what you get for an ethyl group, because you get CH3 next to CH2, so the relative area is 3 to 2, and the splittings, that's a triplet because it's next to the CH2, that's a quartet because it's next to the CH3. So we can very confidently say that peaks B and C together come from an ethyl group. So we have CH2, CH3, where those two hydrogens give you peak B, and those give you peak C. And we can explain that by going through the details. Remember, you've always got to write down how you know that that fits. So you say for B that it has an area of 2, and we know, because we thought about the areas before, that that means that there are 4 hydrogens. So what we're actually saying is not just that we have one ethyl group, but that we must have 2 equivalent ethyl groups. So we have 2 equivalent CH2s. And that's important because what we're then looking at is, remember, 2 things stuck on the aromatic ring, and what seems likely then is that both of them contain an ethyl group. It has a quartet structure, and again, explain what that means. 3 hydrogens on the adjacent carbon, which is that one, and its shift is very important. It has an HCO shift, which is 3 to 4.3 ppm, and you can see it's right at the edge of that. It's about 4.3 ppm. And that's very important because that tells us what comes next in the structure. Because we're saying these hydrogens have an adjacent oxygen, so actually we can put an oxygen on there and say we must have CH3, CH2O to account for the shift of those. And then we can do the same for C. Let's just make a bit of space down here. So C has area 3, which we know means 6 hydrogens, and therefore 2 equivalent CH3s. It is a triplet due to the adjacent CH2. And this one just has an HCR shift, which is 0.5 to 2 ppm, which that doesn't tell you anything useful, but it's still got to be documented so that you can show, yes, that one does fit in with what I'm saying the structure is. So what we're looking at then is that we think that we have a benzene ring with 2 substituents, but we don't yet know how they're arranged. And 2 OCH2 CH3 groups. So the next thing is that we've got to work out what else there must be, because we know there must be something else, because apart from anything else there is a carbonyl peak in the carbon-13 NMR which isn't accounted for by any of this. So the obvious thing to do is to go to the molecular formula, which is C12H14O4, and look at what's left. So here, that is going to be C6H4, because if we've got two substituents there's just room for 4 hydrogens on there, and that gives you C2H, sorry, C4, isn't it, because we've got 2 of them, C4H10O2, and if we add those up we've got C10H14O2, and that leaves 2 carbons and 2 oxygens left over. So we've just got 2 carbonyl groups, basically. 2 carbons and 2 oxygens is all we've got left to account for. And so we've got to fit 2 carbonyl groups into the structure. And really the only possibility then is that they're going to have to come between the oxygen there and the benzene ring, because there isn't anywhere else to put them. There must be something next to the oxygen. If we attached it directly to the benzene ring, where would the carbonyl groups go? So the only possibility is that the carbonyl groups go in between. Okay, so what we know then is that we have benzene ring with 2 substituents, and we have 2 COO, CH2, CH3. Okay, because we've realised that that is the only place we can fit those carbonyl groups in. So the only thing that leaves us then is the question of which isomer do we have. So do we have the 2 versions of that group there, or there, or directly opposite? And we can tell. Not from the Proton NMR, because remember we have to ignore, I mean you can actually tell from the Proton NMR, but we have to ignore that because that's not on the syllabus. But we can tell from the C13. And this you do have to be able to do. So you just look at this and you think, right, for each of these possibilities, how many different carbon environments are there within the ring? So if we have this one, then you can see you have symmetry down there. So that one is equivalent to that one is equivalent to that one, and that one is equivalent to that one. So you're going to get 3 aromatic carbon peaks from that one. If we had this one, then we have symmetry down there. So this time we're going to get 4 peaks, because that one's unique, this one is equivalent to that one, this one is equivalent to that one, and this one is unique. So that's going to give 4 of those peaks. If we had this structure, then you get symmetry down there, but you also get symmetry across here. So what that means is that this one is equivalent to this one, because it's reflected in there, but all 4 of these are the same, because they're all in the same environment, because this one is reflected in there to produce that one, or reflected in there to produce that one, and all 4 of those are the same. So that would only produce 2 peaks, and therefore that one is the only one that accounts for the fact that we have 3 peaks in the spectrum. Now this of course only applies because these 2 substituents are the same. If we had 2 different substituents, then most of the symmetry is gone, and you would get 6 peaks here, 6 peaks here, but still fewer here because you still have some symmetry. But when you have 2 equivalent groups substituted, by just going through this thought process you can work out which isomer it is. So it's got to be that one. And so that gives us our final answer then, which is that the structure is benzene ring with its 4 hydrogens, hence there, and then 2 of these, whoops, missed out the oxygen, 2 of these substituents, like that. And that fits everything, so that's your final structure.